All right, we've learned the basics of chemical reactions. Now let's look at balancing equations. So the law of conservation of mass says that mass cannot be created or destroyed in a chemical reaction. Therefore, for each element in the chemical reaction, the number of atoms you see on the reactant side has to equal the number of atoms you have on the product's side. That is what makes an equation balanced. When you're balancing equations, it's important to change the coefficients. You do not change the formulas. We spent a long time making sure that we wrote the correct formula for a substance. You don't change the formula when you're balancing. You only change that coefficient, that number out front. So, how do we write a balanced equation? Step one is to write the unbalanced equation. Make sure all of your formulas are correct. Next, count the number of atoms of each element on each side of the equation. Then, change the coefficients to make the number of atoms on each side equal. It's important when you've got subscripts to remember that you're going to have to multiply the coefficient times the subscript to figure out the number of atoms. At the end, you're going to want to check your coefficients to make sure that they're in the lowest possible ratio. Just like with fractions in a math class, you don't tell your teacher that the answer is 2/4. You reduce the fraction to the lowest ratio. You're going to do the same thing with the coefficients. And you should always double check in the end to make sure your atoms actually balance. So let's do a simple practice exercise. Aluminum and copper-2 chloride produce copper and aluminum chloride. So step one is to write the unbalanced equation. So here is an unbalanced equation. I've got the correct formula for aluminum. It's not a diatomic element. I've got the correct formula for copper-2 chloride because copper-2 has a charge of +2 and chloride has a charge of -1. I've got the correct formula for copper. I've got the correct formula for aluminum chloride because aluminum has a charge of +3 and chloride has a charge of -1. So I need 3 chlorides to balance out the +3 charge. So I'm going to list all the elements that I have in the equation, aluminum, copper, chlorine, and then I'm going to count up how many I have on each side. I've got 1 aluminum on each side. Well, that's good. That looks balanced. I've got 1 copper on each side. Yay, that looks balanced. Uh-oh, the chlorines are not balanced. I've got 2 on the left and 3 on the right. So I'm going to need to do something to make those numbers the same. Here it's helpful to be comfortable with least common multiples. If you see that you've got 2 and 3, the lowest number that will, the least common multiple for 2 and 3 is 6. So I'm going to be aiming to have 6 chlorines on each side of the equation. How do I do that? I can write the coefficient 3 in front of the copper chloride, and that's going to update my numbers. So now I've got 3 coppers and I've got 6 chlorines. Notice that we did 3 times 2 is 6. That's where that 6 comes from. And on the right side of the equation, my coefficient in front of the aluminum chloride is going to be 2. So that I'm going to have 2 aluminums and 6 chlorines. Again, it's because 2 times 3 is 6. Aluminum doesn't have any number next to it, so the implication is that there's just 1 aluminum there. All right, great. The chlorines are balanced, but I made my coppers unbalanced and I made my aluminums unbalanced. So now we have to go back and fix that. So let's fix the aluminum by writing a 2 in front of the aluminum on the left side. So now I've got 2 aluminums total. And we need to fix the coppers on the right side by writing a 3 in front of the copper. And now this is a completely balanced equation. Here's another example where you don't have to worry about writing the correct formulas because they've been written for you. Again, we're just going to make a list. What elements do I see here? Do be careful with the L's and the I's. I try to be careful on the worksheets that I make for you so that it's clearer when there's a capital I versus a lowercase l. So there, I'll make the capital I's a little bit more clear for you. I've got aluminum, iodine, mercury, and chlorine. Let's do a quick tally. 1 aluminum on each side, 3 iodines here, just 2 on this side, 1 mercury, 1 mercury, 2 chlorines, 3 chlorines. Not balanced in terms of iodines or in terms of chlorines. Again, with the numbers 2 and 3, the least common multiple is 6, so that's the target number I'm aiming for. I need 2 here, so I'm going to update my numbers. And now I want to balance the iodines over here, so I'm going to write a 3 there. So now I've got 3 mercuries and 6 iodines. Now well, my chlorines need to be balanced as well. Again, the least common multiple is 6. So I'm going to write a 3 here. 3 times 2 is 6. But I need to update my mercuries as well. And I'm going to write a 2 in front of the aluminum chloride. 2 times 3 is 6. And now I have 2 aluminums. So this is now a correctly balanced equation. What I do want to point out to you is if somehow you made a mistake, if you came up with the numbers 4, 6, 4, 6, those numbers are not in the lowest ratio. They're all divisible by 2. So although this is a balanced equation, it would not be considered a correctly balanced equation because you don't have the lowest possible ratio of coefficients. So you would need to go through and divide everything by 2, and this would be the correctly balanced equation. So some tips to help you out when you're doing this. Do balance one element at a time. Focus on one thing so that you don't lose track of where you are. And then after you've added or changed a coefficient, update all the atom counts at that time. Everything that's been changed by changing that coefficient. If an element appears more than once per side, my recommendation is that you balance it last. So for instance, in this example, we have a compound that contains carbon and hydrogen, and then just elemental oxygen. And then on the product side, we have carbon and oxygen, and then we have hydrogen with oxygen. So oxygen appears twice on one side of the equation. Therefore, it's a good strategy to leave it until last to balance it. So my elements are carbon, hydrogen, and oxygen. My counts are 3, 8, 2. Let's see, there's 1 carbon, there are 2 hydrogens. The oxygen is a little tricky though because I have to count these 2 plus this one, so I've got 3 total. So just make sure when oxygen appears in more than one place to remember to add all of it together. So we're going to leave oxygen for last. I'm just going to go ahead and go in CHO order. I want to have 3 carbons, so I'm going to write a 3 in front of my carbon molecule. And now that changes the oxygen. So now I've got 3 times 2 is 6, plus 1 is 7. Next, I'm going to balance my hydrogens. In order to get 8 hydrogens, I need to write a 4 in front because 4 times 2 is 8. So now I update my hydrogens, but this compound also contains oxygen, so I need to update the oxygen as well. Okay, 3 times 2 is 6. Plus 4 is 10. So I've got 10 oxygens total. Now, the only thing that's left unbalanced is oxygen. I'm too low on this side, so I need more. What times 2 equals 10? 5 times 2 equals 10. And so this is now a correctly balanced equation. Some more tips. If you see a polyatomic ion on both sides of the equation, balance it as a single unit. What I mean by that, in this example, I have sulfate ions and sulfate ions on both sides of the equation. I have hydroxide ions and hydroxide ions on both sides of the equation. Rather than trying to keep track of separate sulfur and oxygen atoms and oxygen and hydrogen atoms, you can balance those as a single unit. So I would look for balancing aluminums and sulfate ions as a whole, as well as calcium and hydroxide ions as a whole. You can balance these the traditional way by splitting out the elements, but it is quite a bit faster to keep the polyatomic ion together as a single unit. So let's do a quick tally. Let me show you how that works. 2 aluminums, 3 of the whole sulfate ion, 1 calcium, and 2 of the whole hydroxide ion. Then I have aluminum, 1 aluminum, 3 hydroxide ions, 1 calcium, and just 1 sulfate ion. So in order to balance, I want to have 3 sulfate ions, so I'm going to write a 3 in front of the calcium sulfate. That updates the sulfate, but I need to update the calcium as well. Now, pick something else to balance. My aluminum's not balanced, so I have 2 aluminums on the left, so I need 2 on the right. That's 2 aluminums, but now I have 2 times 3 is 6 hydroxide ions. I am balanced for aluminums and for sulfates, but I'm not balanced for calcium or hydroxide. So if I need 3 calciums, I need to write a 3 in front. 3 times 1 is just 3 for the calcium, but I need to do 3 times 2 is 6 for the hydroxides. So now this is a completely balanced equation, and when I balanced it, I kept those polyatomic ions together as a single unit. One thing that comes up with trying this strategy with the polyatomic ions, keeping it together as a single unit, you need to be aware that a lot of times when hydroxide appears in an equation, it combines with hydrogen ions to form water. So in this example, it looks like the hydrogen ion disappears. It looks like there's no hydrogen ion here on the right side of the equation. But if you think of water as being H with OH, a hydrogen ion with a hydroxide ion, then you can still use this strategy of keeping the polyatomic ion together as a whole unit. But just wanted to let you know that that often happens with hydroxide ions. More tips. Coefficients must be whole numbers. Okay, you can't use fractions. If you ever want to use a coefficient like 3.5, however, don't give up and just start over. Stick with it, and then when you finished, go ahead and double everything. So for instance, this often happens with this type of chemical reaction. These are called combustion reactions, which we'll learn about soon. Here I have a hydrocarbon, which is made up of carbons and hydrogens, reacting with oxygen to form carbon dioxide plus water. So if I go through the trouble of balancing this with my CHO, let's see, 2 carbons, 6 hydrogens, 2 oxygens, 1 carbon, 3 oxygens, 2 hydrogens. Then I start balancing. Okay, I need 2 carbons. Remember, I'm going to leave oxygen for last because oxygen appears twice on the right side of the equation. 2 carbon dioxides. I've got 2 of those, and I've got 2 times 2 is 4, plus this extra is 5. I want to balance the hydrogens now. So 6 hydrogens, so I need to write a 3 here because 3 times 2 is 6. And now I have to also update my oxygens. 2 times 2 is 4, plus 3 is 7. So 2s, 6s. How do I get 7 oxygens? 7 is an odd number. Anything I write in front of the oxygen is going to get multiplied by 2. So I want to write down the number 3.5 here. But the rule is that coefficients must be whole numbers. 3.5 times 2 would be 7. This would be balanced, but it's not a correctly balanced equation. However, I don't have to start over from scratch. What I can do is go ahead and multiply everything by a number that would make all of my coefficients whole. So I'm going to go ahead and multiply everything times 2. 1 times 2 is 2. 3.5 times 2 is 7. 2 times 2 is 4. 3 times 2 is 6. So now this is my correctly balanced equation. So here's some more practice for you to try. Pause the video and then come back and check your answers. Okay, so 5 isn't quite correct yet. We'll look at that in a moment, but 3 has been correctly balanced, 4 has been correctly balanced. 5 is balanced, but not correctly because of this fraction that I have here. So this is one of those situations where you do need to go back and double everything. So the 1 becomes 2, the 4.5 becomes 9, the 3 becomes 6, and the 4 becomes 8. I hope this helped.